Okay, good afternoon, guys. Let's get our books open, please. Sorry, that was rude of me. Good afternoon, everybody. Good afternoon. Didn't mean to interrupt you. Thank you. Let's get our books open, please, to the work you were doing yesterday. It was questions 10, 11, and 12 in your textbook on page 76, where you're finding this thing which we call the derivative. And all the derivative is an expression. It's also a function. But when you start to get immersed in what the graph of the function of the derivative looks like and what it means, it doesn't really mean too much. The function itself as a formula is a device that you can use or a tool that you can use to find the slope of a tangent to the original function whose derivative you're talking about. And the formula for the derivative is given up here. This is using Lagrange's notation of the prime notation, so we can call it f prime of x, or you can call it y prime. Regardless of the notation you use, you have to use the function notation in the definition of the derivative. It's the limit as h approaches 0 of f of x plus h minus f of x all over h. And whether you use Lagrange's notation of y prime or f prime of x, or you use Leibniz's notation of dy dx, or d dx of y, or d dx of f of x. And by the way, you can pronounce this in a number of different ways. You can say that this is the derivative of y with respect to x, or you can say this is the derivative with respect to x of y. It doesn't really matter. Or, I don't know anybody that uses Newton's notation, but that x with a dot over top, I don't know what he was thinking. There must be some reason for that. There must be some logical reason that he's doing that. Regardless of how you do it, that's the formula for finding the derivative. So take a look at your work, please. Does anybody have any questions you would like me to go over? Enrico? 12C? Yeah. Okay, so we have x plus 1 over x. And when we use the limit formula, it will be the limit as h approaches 0 of f of x plus h, which would be x plus h plus 1 over x plus h, and then minus f of x, which is x plus 1 over x. And don't forget, this is all over h. And I think looking at you, you're okay with the setup, right? So now the question becomes, what do we do with this? And what I would do is I would multiply the entire top and the entire bottom by x and also by x plus h. And the reason I'm doing that is that when I multiply x times x plus h by 1 over x plus h, this x plus h and that x plus h will cancel. Now, when I multiply the x plus h over here, this term, when I multiply this term by the x and the x plus h, nothing cancels, so I'm going to have to multiply out that result when we get to that stage. All right, so, yeah, you got to keep writing limit as h approaches 0. We have the limit as h approaches 0 of x times x plus h squared, because I'm multiplying that x plus h in the first term. I'm multiplying this thing by both of these, so that gives me the x and the x plus h. Then I'm going to end up with plus simply x, because what happens is when I multiply this term by this, the x plus h cancels. Then I'm going to have, and I really dislike what I've got written here, not because I've made a mistake, but that's where my mind is right now. It's minus x minus 1 over x. So when I multiply the x by the x and the x plus h, I get minus x squared times x plus h. And when I multiply the 1 over x by the x and the x plus h, the x's cancel, and I'm left with minus x plus h. This is all going to be over h, and I want to double check all of my multiplication by just standing back and looking at it for a second. I should have x times x plus h squared, and I do. I should have plus a single x, and I do. I should have minus an x times an x plus h, and I do. And I should have minus an x plus h in brackets, and I do. On the bottom, and this is a very common mistake, I almost just made it. On the bottom, we also have that stuff, right? It's very common to forget about that. And then you get to the end and you go, what did I do wrong? So we also have an x and an x plus h here. Now we're going to clean up the top, and I'm going to just take a detour here. And I'm going to use scrap paper to figure out what this first term is. I don't want to have to rewrite the whole thing at each step. When I FOIL out these two binomials as a product, I get x squared plus 2xh plus h squared. And I need to multiply that by x, which is going to give me x cubed plus 2x squared h plus xh squared. I want to double check that. It will be x cubed, it will be 2xh, and the x will be squared, and it will be xh squared. I think that looks okay. So going back over here, I'm just going to rely on my memory, but I also have 18, 22 minds behind me. You can remind me if I make a mistake here. This is the limit as h approaches 0. This first thing was x cubed plus 2x squared h plus xh squared. I have plus my x. I have minus x cubed. That's kind of making me happy because I had an x cubed out front, and I can't have any terms left unless they have an h. I have minus x squared h. I have minus x, and I have minus h. And again, and it's not just because I'm teaching, it's because I'm doing math at this level. I'm just going to stand back and double check all that. You said the first three terms were right, and then I have plus my x. And I'm literally scanning my eyes left to right, slowly, making sure I don't miss anything. Minus x squared times x, which is there, it's x cubed, minus x squared times h, which is there, minus my x minus my h. Good. So what happens to the top here? We have x cubed minus x cubed. We have x minus x. I have a couple of terms that have x squared h in them. Right? I have this term, which has x squared h's, and I have this term, which has x squared h's. So I might as well put them together. 2x squared h minus x squared h is only 1x squared h. We're at the limit where h approaches 0 of, we said 1x squared h. So I've taken care of those two blue highlighted terms. I have plus an xh squared. I have minus an h, and I think I've got every term accounted for now. And you really want to be careful about that, because, of course, if you miss one, it's wrong. Over that. And we have, Enrico, one more step to complete before we can go ahead and put h equals 0 in, and that is to factor h out of the top to cancel with the h on the bottom as a factor. This becomes the limit as h approaches 0. I take an h out. I'm left with x squared plus xh minus 1. Over h, x, x plus h. Does that look okay to you guys? The h's cancel, and now I can go ahead and put 0 in. It's at this point where I go and substitute in that I stop working down. I just go off on the side and do it. It will be x squared plus x times 0 minus 1 over x times x plus 0. which gives me x squared minus 1 on the top and x squared on the bottom. And I know that that's not the answer they have in the back. They have it written in a different way. But it's equivalent. And there's two ways to look at it. If you take, they must have 1 minus 1 over x squared.
Yeah.
If you take and you use a common denominator, I'm going to multiply the top and bottom of this first term by x squared. And I'm going to get that.
Okay, I was just confused because I had that answer, but it was written differently, so I was confused.
Conversely, and I always use numbers to explain this, if I had 7/3 minus 4/3, the reason it's 1/3 is, I'm going to go 13ths. If I have 7/13 minus 4/13, the reason it's 3/13 is because when you have a common denominator, the rule, and I don't want to explain why the rule works, but the rule is that the denominator stays the same. And to get to this stage, you first do this, correct? So there's nothing wrong with going the other way. If 7 minus 4 over 13 is 7 over 13 minus 4 over 13, then x squared minus 1 all over x squared is x squared over x squared minus 1 over x squared, which leads you to the answer they have in the back. By the way, this is a preferable way to write it. We would rather have one single fraction as opposed to a whole bunch of terms added together, if at all possible. Okay. Other questions? Oh, I did that already. All right. So we're going to move on today and start learning about the rules for differentiation. And today we're actually going to look at 1, 2, 3, 4, 5 or 6 different rules, but they're very, very closely knitted together. They're very, very close to being the same rule. And the rules of differentiation allow us to avoid the definition of the derivative, which is that limit equation. If we can avoid doing that, it's preferable. We're going to, in the end, find derivatives today without using limits. Okay? And we're going to have to correctly interpret what those derivatives mean. So to begin with, as a warm-up, this question, and I think understanding the question is just as important as knowing the answer to the question. Not just because you need to understand it to answer it. I mean, it's really, really important you understand the language. This says, why is the derivative of a constant equal to 0? In other words, one way I could ask this question is, if f of x equals a constant, why does f prime of x equal 0? That's one way I could ask it. Or I could say, show that d dx of a constant is 0. And all three of these things are saying the same thing. Well, the easiest way to explain this is to talk about a graph where you have y equals f of x and f of x is equal to some constant. Now that constant can be any number we want. It could be pi. It could be -3. But the bottom line is that function will look like that. It will be a horizontal line, and that horizontal line will be at C. Right? I guess I could put that in there. I don't want to crowd things too much, but this y coordinate of this intersection point is C. So if we go to the meaning of a derivative, which is supposed to be, and is in fact, a way to calculate the slope of the tangent or the slope of the function wherever you want, the slope of a horizontal line is 0. So if I were to make a table of values, and say to you, calculate the slope of this line when x is 7, you'd go up here to 7, you'd say, well, what's the slope of the line at x equals 7? You'd say it's 0. If I said, what is the slope of the line over at -pi? You would say 0. In fact, because it's horizontal, that's the precise meaning of a horizontal line, is that it has a slope of 0. The derivative must be equal to 0 everywhere, which means the derivative is not equal to a function of x. You don't have a function of x that you use to calculate the slope because the slope is always the same thing, 0. So that's one way we could explain why the derivative with respect to x of a number is 0. So we could say the slope, which is a derivative, is always 0. So dy dx equals 0. It's a horizontal line. We don't have to do it that way. That's more of an intuitive approach. We could prove it. And we're going to be doing a proof here right away for something else. That's by far the one comment when I talk to former students. What are you doing in university calculus that's new to you or that you wish we did more of in high school calculus? And the answer is always proofs and theorems. And I'll warn you right now that with proofs and theorems, it isn't so much important that you could do them on your own. It's important that you can follow them. Okay? But the proof here, we can prove this. This is not a proof. This is just kind of intuitive reasoning. We could say that if f of x equals some constant, the derivative, I'll go with f prime of x here, is the limit as h approaches 0 of f of x plus h minus f of x all over h, right? That's how we find the derivative. Now, what is, I'm going to fill in one part of this for you. We've got f prime of x equals the limit as h approaches 0. What is f of x equal to? Well, f of x is c, right? Now comes the interesting question. What is f of x plus h equal to? What's f of 5 equal to? It's equal to the constant. Not 0, that's the slope, right? If I made a table of values here for the function, not the derivative, for the function, it doesn't matter what any of these values of x are, the function will be equal to that constant. So not only is f of x equal to c, but f of x plus h is equal to c. F of anything is equal to c because the function itself is a constant. So what we end up with is the derivative of the function, in this case, is the limit as h approaches 0. Now, can I put h equals 0 in right now? The answer is no. Okay? But when I take c minus c and get 0 over h, I still can't put h equals 0 in. However, zero over h is 0. And now I can put h in. And I know that seems like a fanciful thing to say, that I'm going to put h equals 0 in there, but I just did it. There's no h in there, so me putting h equals 0 in there is done. Another way I can explain to you why this limit is equal to 0, we already talked about. It was when we first learned about limits, and I think I even remember the exact limit. I think this was it. What's that equal to? 32. Because it doesn't even depend on x, so the value, which we can talk about because 32 is continuous, the value is the value of the limit, and the value is 32. The limit of a constant is the constant. So what we have done here is we've done actually a proof that the derivative of a constant is 0. All right, now what we're going to do is we're going to prove how to find the derivative of x to a power. Now, what this means I would like to show you what it means first. And I will warn you that when we do the work, it's going to go edge of the page to edge of the page. So you might want to write this little table that I'm going to show you down near the bottom. Okay? But what this is saying is when you differentiate x to the n, oh, there's a new word, differentiate. Differentiate means to find the derivative. When you differentiate x to the n, you get n times x to the n minus 1. What does that mean? It means that if y is equal to x to the 10, then the derivative of that is equal to 10x to the 9. It's this thing that we have already talked about informally. And I've never actually written it down. I've just informally talked about it. It means that if x is x to the 9, the derivative of x to the 9 is 9x to the 8. If it's x to the 4, the derivative is 4x cubed. That's what this is saying. I mean, take a look at this. It's saying the derivative with respect to x of x to the n is n x to the n minus 1. And I want to make a point here just for later. What we're doing in going from here to here is differentiating. It's a verb. It's an action. We are doing something. We are differentiating. So that's why we say the derivative of x squared is 2x. We do something to it. So now we're going to prove that. But before I prove it, I'm going to review the binomial theorem. Okay? For those of you that have taken Math 30. For those of you that have not taken Math 30, hands again, please. I know I should know this, but just by a show of hands, who has not taken Math 30 yet? Not you may be in it right now, but you haven't completed it. Okay, so you guys are over there. So you will learn something here about something that will be very important for Math 30. And this has to do with the binomial theorem. So we know, well, and then before I review the binomial theorem, I have to review something else, which is combinations. If I take a look at the following thing, what this means is 4 choose 2. And what that means is the following. It means that if I had 4 people, I have Alice, Betty, Charles, and Danny. Okay? I know that's very creative. I have 4 different people, and I'm going to choose 2 people to go for ice cream. I'm going to take 2 people to go for ice cream. Well, can't we all go? Sorry, life is hard. I don't have that much money. It's just 2 of you. Okay? How many ways could I choose 2 people? Well, this is a pretty small set of people, so I could choose Alan and Betty. I could choose Alan and Charles. I could choose Alan and Danny. I could choose Betty and Charles. I could choose Betty and Danny. Or I could choose Charles and Danny. I think that's it, isn't it? I don't think there's any more ways to do this. So the answer is 6. There's 6 ways that I can choose 2 people out of 4. And there's a function on your calculator that can do that. But the bottom line is that's what that choose means. So when I look at 5 choose 2, do that for me. I think it's 10. It's either 10 or 15. Or maybe it's neither. I don't know. It's 10. That means that if I had, I have 5, it's Halloween, and I have 5 bowls. I have a bowl of mini Snickers. I have a bowl of Reese's Pieces. I have a bowl, and the little kids walk up, and they start grabbing everything. It's no. You can only get 1 of each. Can I get 2 Snickers? No. You have to take 1 from one bowl and 1 from another bowl. The number of different choices that they could make would be 10 because you're choosing 2 out of 5. Okay. So now I'm going to review the binomial theorem. If I asked you to expand x plus y cubed, then without using the binomial theorem, you would have to take x plus y times x plus y times x plus y. And I'm going to do this really quick. You would FOIL this out. Then everybody in this first polynomial would dance once with everybody in the second. So you'd go x squared times x squared times y. Move on, 2xy times x. Gives 2x squared y. 2x squared times y gives 2xy times y gives 2xy squared. Moving on, I get an xy squared, and I get a y cubed. Did I get them all? I went pretty quick there, but I think I did. So what do you get? You get x cubed plus 2x squared y plus 2xy squared plus y cubed. Okay. Now, it turns out that there is a way that I can go through this and do this without foiling it out. Did I write something down wrong? It should be 3. Absolutely. Thank you. And it turns out that this first term is 3 choose 0 times x to the 3 times y to the 0. I mean, y to the 0 is 1. And 3 choose 0 is saying I have 3 different cookies up here, and you get to choose none of them. How many ways can you do that? 1. You just look at them and it's done, right? It turns out that this is 3 choose 1, x to the 2, y to the 1. This is 3 choose 2, x to the 1, y to the 2, and this is 3 choose 3, x to the 0, y to the 3. And the pattern here is that that exponent of 3 tells you about these coefficients. 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. And when you get to the end, you're done. 3 choose 3, you can't choose any more than 3. The number on y's exponent always matches how many you're choosing. Is this coming back now? And the number on x's exponent has to add to the number on y's exponent to give you, in this case, 3. So if I said to you, take 2x plus 3 raised to the 4 and expand it, we can use the pattern. You can say it's 4 choose 0. It will be 2x and 3. This number that is on the choose, goes up top here. And the number that goes on the first part is a number that when added to that key number gives you the total of 4. So that's 4. Your next term would be 4 choose 1, and then you just go 2x to the 3, 3 to the 1. You just keep increasing the green number by 1 each time you go forward, and you knock 1 off of the x until finally you're left with no x's. So it's a way to expand a binomial very readily. The third term would be 4 choose 2. The 3 would be to the 2. The 2x would be to a 2 because 2 plus 2 gives you the 4. Then we would have 4 choose 3. 2x to the 1. 3 to the 3. And then we would have 4 choose 4. 2x to the 0. 3 to the 4. And there's all kinds of other things we talk about in Math 30, like the fact that it's an exponent of 4 on the binomial, but you get 5 terms. There's other patterns involved, but that's how you expand a binomial. And the reason why we're going to have to learn about that is what we need to do is apply the limit formula to x to the n. So let me go to a fresh page here. What we need to do is find the derivative with respect to x of x to the n. Or if you like, if f of x equals x to the n, what is f prime of x? That's what we were asked to do. So what's all this talk about the binomial theorem? We talked about combinations because combinations are needed to understand the binomial theorem. When we put this information into the formula for the derivative, which is the limit as h approaches 0 of f of x plus h minus f of x all over h. So now we're doing the question. We're going to get the following expression. And you're going to want to start writing on the left-hand side of the page because not this line coming up, but the one afterwards is going to be very long. This becomes the limit as h approaches 0 of x plus h to the n minus x to the n over h. And we've done these questions before. If it was x squared, then you would take x plus h times x plus h, you'd multiply it out. And then remember, everything goes away except for the terms that have h's. Right? If it was raised to the 4, you could actually multiply it out. The problem here, and I know where you're coming from, you look at that and you're probably saying, well, how do we expand out x plus h to the n when we don't know how many there are? Well, let me show you. So this is going to be equal to the first term in the expansion of x plus h to the n will be n choose nothing x to the n h to the nothing. That's your first term, according to the binomial theorem. Now, in the binomial theorem, and I can certainly go back and show you a specific case, forget about the coefficient. Look at what happens here to the exponent on x. It starts off being 3, which was the number that we had for the exponent on the whole thing. Then it becomes 2, then it becomes 1. It goes down by 1 each time. Whereas the number on y started off at 0, and it went up 1 each time. This, the number you're choosing out of the 3, always matches the number on y. So we have a pattern, and what we can do here is say that the next term in this will be, oh, and I've made a mistake. It's a pretty significant one. Let's see if anybody can find it. I'll give you a hint. It's a limit as h approaches 0. And that is a serious mistake. Okay. My next term will therefore be n choose 1. It will contain one less exponent on x than it did before, which means the exponent on x now will be n minus 1. Which seems a little weird. We're used to seeing a number up there, but it's not a number, it's n minus 1. Well, it is. It's just a number that depends on what n is. And we will also have an h, which has an exponent that matches the number we're choosing out of n. That's the second term. Now, given that there could literally be hundreds of terms, we could go on forever. We're not. We're going to do one more, and then we're going to do the last 3 terms. And we'll just put dot, dot, dot for everything that's in the middle. Okay? So the next term would be n choose 2, we would have x to 1 less even than it was, which would be n minus 2. And then, of course, h becomes to the 2. And then we have dot, dot, dot. Now, if you have enough room, what you have written so far for this, you're going to have just as much room beside it to continue. I don't. And you don't have to erase it and squeeze it in. What I'm going to do is just continue what I wrote down here. Okay? But you need to plan out your space here. My very last term. Take a look at this. What is my very last term? My very last term is n choose n, x to the 0, y to the n. Which means my very last term here will be n choose n, x to the 0, h to the n. Now, what is my term immediately before it? Okay, so I know when you go left to right that the number you're choosing falls or grows by 1 each time, right? So this is a 0, this is a 1, this is a 2. We're always adding 1 to move forward. And that key number that is on the choose is the thing that's on h. So another way to put it is the exponent on h goes up by 1 each time, which means the exponent on h here must be 1 less than what it was. You're really going to have to roll that around in your head. What do you do to this number to get this number? What is it you do to the yellow number to move forward to the green? You add 1. We take the yellow number and we add 1 to get, and we add 1 to get the green number, right? Yellow to green is add 1. If you add 1 to n minus 1, you get n. The x will be to the 1, because these two exponents have to add up to give n. And now we're starting to wade into some deep water here, which is why I said to you, I don't know that it's important you could do the theorems or proofs on your own, but you should be able to follow them. I'm going to have an n choose something here, and it will be choose n minus 1, because these two numbers always match. The exponent on h always matches the key number, what we call the key number in math, which is the number you're choosing from. And if we go one more to the left of that, we would have n choose n minus 2, x to the 2, h to the n minus 2. And you don't even need dot, dot, dot there because you have it here. Now, but wait, that's not the top of our limit expression. The top of our limit expression is x plus h to the n, which we just wrote out, minus x to the n. So we can't forget about that minus x to the n. We also have minus x to the n. This whole thing is on the top. And back in the days of whiteboards and chalkboards, I would just start on 1 and I would just write it. It would be on one nice line. Okay? If you write small enough, you could probably fit it on one line. This whole thing now is over h. Whoops. Now the rest of this proof is not difficult, but you need to follow it along carefully. The first thing to note is that this is x to the n. N choose 0 is 1. I don't care how many people you have. If you're going to choose none of them because you don't like any of them, there's only one way to do it. It's to leave the room. Okay? N choose 0 is 1. H to the 0 by definition is 1, so you're left with x to the n. That is very good for us because we have minus x to the n, and we cannot be left with any x's. I want you to notice now that if you look up here at the second term term contains an h, doesn't it? And so does the third, and the fourth, and the fifth, and the sixth, and the seventh, and the eighth, and the third to last, and the next to last, and the last. They all contain h, which means we can factor an h out. If it's lost on you, I want to point out that x to the n minus x to the n is a wash. It's gone, right? They no longer play a role in what we're doing here. So now we're going to have the limit as h approaches 0 of, I'm factoring an h out. So what will I have left? I will have n choose 1 times x to the n minus 1 plus n choose 2 times x to the n minus 2 times h, because it was h squared. And I see that when I grouped it, the software hid the number. There's a 2 there, right? So when I factor the h out of my first term, which is this one, I don't have an h. When I factor out of my second, which has an h squared, I'll have a single h. Plus, I'll have n choose 3 times x to the... I'm actually going one further here that I didn't write. The next term would be to the n minus 3, and it would have an h squared. Do you agree that normally this would have h cubed because it's choosing 3, but I'm factoring h out? Here's the important thing, and I don't think a prof in university would do this. Every other term to the end, I don't care how many terms there are, when you factor that h out, you're going to be left with some h's. Right? The only term that is not going to have any h's is the first term. I just want to clean that up a little bit. So this is all over h, and we're almost done, really. We cancel these h's, and now I'm allowed to put h equals 0 in. So this is where I'm subbing h equals 0. What am I going to get? I'm going to get n choose 1, x to the n minus 1, plus 0 plus 0 plus 0 plus 0, on and on and on. Because when I put h equals 0 into this term, for example, right here, well, I'll get 0. Because there's an h there. I'm multiplying by h. The third term, which is really, yeah, it is the third term. The third term contains h squared, so it's going to have a 0. The fourth term will have h cubed. They're all going to have h's. So what I am left with is, don't forget, this was the derivative with respect to x of x to the n. I'm left with n choose 1, x to the n minus 1. But what's n choose 1? N. It's n. Now, n choose 0 is 1, but n choose 1 is n. If I have 22 people in the room, and I have a Tim Hortons gift card, and I don't want it, I'm going to give it to somebody, I have a choice to make. I have 24 choices. So 24 choose 1 is 24. I don't have a Tim Hortons gift card. Sorry. So this means that we have proven the derivative with respect to x of x to the n equals n times x to the n minus 1. Which is what we were asked to prove, right? Remember, the meaning of that, I guess it's back here, is in this table. It simply means if you have x to the 11, you move the 11 in front, you drop 1 from the exponent. Okay, there are other rules. Are you going to be asked to prove that on an exam? No. Are you going to be asked to use it on an exam? Absolutely. There are other rules. So here are all of the rules that we need to be aware of today. The derivative of a constant is equal to 0. I've already talked about that. The derivative of x to the n is n times x to the n minus 1. This is the main rule today. The derivative of, this is an important one, the derivative of a constant times a function is the same as the constant times the derivative of the function. So, even though I didn't give you a rule for differentiating this, what this rule that you're looking at now says is the derivative of 4 times x to the 7 is 4 times the derivative of x to the 7. That's all it means. And this will become very useful when we get very complicated problems where you have a constant, and what you want to do is go just, you know what, let's just put the constant over here. Let's differentiate the thing and then put the constant back in. So what we would get here would be dy dx, and I love this notation. The other notation for me to explain this to you is very awkward, is 4 multiplied by 7x to the 6, which is 28x to the 6, which is kind of what we discovered, right? You move that number down in front and multiply. In fact, your textbook and calculus textbooks in general give this as a special rule. What is the derivative of a constant times x to an exponent? It's the constant times the old exponent times x raised to 1 less than the old exponent. And that's why I believe in your notes, I may even say, maybe I don't, I've got it up here, Rule 4 is really just these two rules put together. That's all. There's also sum and difference rules, and we want to be very careful here about sum and difference rules in math. I'm going to use two examples from Math 30. Not on your life. No way. No way is the sign of a sum the same as the sum of a sign. It isn't. There's a special identity for that. I can go back to grade 10 math. Is a plus b quantity squared equal to a squared plus b squared? No. The square of a sum is not equal to the sum of the squares. There's very few mathematical operations where that is true. Derivatives are one where it is. The derivative of a sum is the sum of derivatives. So if I say to you, what is the derivative with respect to x of x squared plus x cubed? Well, it's the derivative with respect to x of x squared plus the derivative with respect to x of x cubed. We don't write that every time. You don't. You'd be writing stuff forever. What's the derivative of x squared? Well, 2x to the 1. We've just learned that officially. Plus 3x squared. I don't know anybody that's going to write this. You'll just go from here right to there. You have a question, Nathan, or no? Okay. And it's the same if it's minus. So those are the rules that we're working with. Let's take a look at examples. What is the derivative of y equals 2x plus 3? So I am going to break this down for you. This will be equal to the derivative with respect to x of 2x plus the derivative with respect to x of 3. Right? That's what the rules say. And I'm only going to do this once or twice with you. Okay? Now, what is the derivative of 2x? Well, the derivative of 2x is 2 times the derivative of x. Because, I know you probably don't want to write that. You just want to say it's 2, right? Okay, that's fine. That's fine. But the derivative of a constant times a function of x is the constant times the derivative of the function. And these rules will be necessary later. Okay? You will not always be able to bypass them. So, what is 2? Well, 2 is a constant. What is the derivative with respect to x of x? Well, you take this exponent, this is y, to find dy dx, you move that exponent in front, and you drop 1 from the exponent. And you're left with 1 times x to the 0, which is 1. Plus, what is the derivative with respect to x of 3? Well, we learned in the very first warm-up today, the derivative of a constant is 0. So the derivative with respect to x of 2x plus 3 is 2. And I hope that everybody would just look at that and say, well, of course it's 2. By the way, you get so caught up in calculus and high-level math that you forget to use common sense sometimes. 2x plus 3 is a straight line with a slope of 2 because the coefficient in front of x is 2. So, of course, the derivative is 2. Okay. Take a look at the next one. Well, dy dx, I'm not going to do a lot of explaining here. Dy dx is 15x to the 4 minus 6x squared. Are we okay with that? It's pretty simple, really. It's one of the things in math you'll probably never forget. And I mean that. You'll leave high school and years later, your son or daughter will be doing calculus or you'll be helping somebody. You go, oh yeah, that's where you move that exponent down in front and you drop 1 from the exponent. How do we handle something like 4 root x? You'll notice that I used the binomial theorem in my proof, and the binomial theorem is only good for natural powers of n. It turns out that there are other proofs we could do beyond this course that show it's true for any number for n. Fractions, positive numbers, negative numbers. So all we need to do to begin with is to rewrite this as 4x to the half. That's what we're differentiating. So we bring the half in front, and you get 2. You rewrite the base, and you drop 1 from the exponent. So the 2 in front comes about because I took the old coefficient of 4 times 1/2, which is the old exponent. 1/2 of 4 is 2. I drop 1 from the exponent. We never want to write things at this level with negative exponents, so I'm going to move it to the bottom. Now in this case, we need to move this thing up to the top first and kind of rewrite that expression or rethink how we're viewing it. We want stuff where we have a number in front times x raised to a number. So if it's over x to the 3, we move it to the top and we say x to the negative 3. If it's divided by 2, we put a half out in front. dy dx. By the way, have you noticed that sometimes I'm doing this and writing dy dx, and sometimes I say d dx of the expression? It's the same thing. Okay. Will be negative 4 x to the negative 3 minus 1 x to the 1. You multiply the old exponent by the old coefficient to get the new coefficient. You subtract 1 from the old exponent to get the new exponent. Of course, what we would do now is write negative 4 over x cubed minus x. Any questions with that one? Okay, now the textbook author is wildly inconsistent in what they do. They may leave it like this, or they may put it together with a common denominator. We're going to have to put it together with a common denominator, but that's later. Okay. What do we do here? Well, unfortunately, you have to take 2x squared minus x and multiply it by 2x squared minus x to get a polynomial You don't know how to differentiate this. And if you think you can take the 2 and move it in front and drop one from the exponent, you're wrong. It doesn't work that way. It only works that way if it's x is the base. So we need to take 2x squared minus x times 2x squared minus x and do some foiling. You'll want to check my algebra. Look okay? That's y, which means y prime. Just to keep you on your toes, I'll use different notation. I hate the prime notation, but we use it from time to time. Would be 16x cubed minus 12x squared plus 2x. And after a while, it just becomes such a natural thing. You realize that you've differentiated and you weren't even really thinking consciously about what you were doing. It just flows. Of course, that's where you can make a mistake. Are we okay with that? Again, there are other ways to write this. We should probably factor it, but that's for later. I don't care about the factoring. You could take out a 2x, and then maybe you'd have a quadratic left. Maybe it would be factorable. We'll worry about that later. Okay, so look at this question. This is a question, everybody, that you would have been given a week ago. Find the equation of a tangent to a graph at x cubed minus 1. And what you would have said of x cubed minus 1. What you would have said is you need the coordinates of a point. It's at x equals 2, comma. If I put 2 in here, 7 comes out for y. Am I correct on that? So you need the coordinates of a point, and you need the slope of the tangent, right? So what you would have done a week ago is you would have said, oh, man, the limit as x approaches a of f of x minus f of a all over x minus a. Or the limit as h approaches 0 of f of x minus f of a all over x minus a. That's not what you're going to do here. This will be equal to the derivative of the function at x equals 2. The slope of the tangent is not equal to the derivative of the function. It's equal to the value of the derivative of the function at a certain point. And that's like stealing candy from a baby, because dy dx is 3x squared. That's easy. That's the derivative. Now, another way that I could say d dx when x equals 2 is I could say it's f prime of 2. There's lots of ways I can communicate to you that we need to put 2 into the derivative to find out the slope. So f prime of 2 would be 3 times 2 squared, which is 12. The slope is 12. And now you know the point. So you put 2 comma 7 and the slope in. And we're not done, but I'm done. You could simplify that, and you probably should, but that's grade 7 math, 8 math. Right? Multiply that 12 through, move everything to one side. You would end up with 12x minus y minus 18, 16, something like that. I don't know. It's unimportant. We're not going to do the last example. Okay. I haven't decided whether we are going to tomorrow or not, but we're not going to do the last example today. Okay. I have a feeling what's going to happen is one of the questions in your assignment, example 3 or 4, one of the questions in your assignment are going to be very closely related to 3 or 4. You don't need to, now we're getting into stuff where I'm saying you don't need to do every single question. I mean, I think there's a question there where it just goes on and on, find the derivative, find the derivative, find the derivative. Make sure you know how to find the derivative. Take a look at some of the word problems near the end of the assignment. and we'll go over everything tomorrow. Tomorrow we will look at something called the product rule, because even though the derivative of a sum is the sum of the derivatives, and the derivative of a difference is the difference of the derivatives, not so for a product or a quotient. The derivative of a product is not the product of the derivatives. There's a special rule. So get to work on some of that. You've still got about 12 or 13 minutes left.